In this lesson, we're going to look at more complex motion, two-dimensional motion, and in order to do that, we want to first review 2D vectors, or vectors in general. So if you recall, vectors have magnitude, or an amount, and they have direction, or which way they're pointed. So we can break a vector into what we call components using trigonometry. So if I have a vector like this, that we'll say is, what I'm going to call it, let's call it velocity. So I have some velocity vector like this, and it's at some angle theta. Well, we know that the x and y component, we can make a right triangle like this. So my v subscript x, meaning my velocity in the x direction, will be v times the cosine of theta. And my y will be v times the sine of theta. And this is because sine of theta is also equal to the opposite over the hypotenuse, so vy over v, which can be rewritten as vy equals v sine theta. Same thing for x and cosine. So in other words, you can break up, if you know this lower right angle, you can break up into components using sine and cosine. If you knew the upper angle as, say, phi, well, then this would be vy would be equal to v cosine of phi. So it depends on what angle you know, and you have to be a little bit clever and careful with your trigonometry, but I'm just pointing out it's not always that one direction is sine and one direction is cosine. It depends on what angle you know. But once we're done with, working with things, we can also take components. Say I have a vx like this, an x component of velocity here, and a y component here. We can combine them by saying that this is the square root of vx squared plus vy squared. And we can say that theta is equal to the inverse tangent of vy over vx. So we can use trigonometry to combine them back together. So how does this all play out into 2D kinematics? Well, what we want to do is, as long as we use perpendicular components, so for example, x and y, any motion that happens in the x direction is completely independent of any motion happening in the y direction. So I can do all the math I want with x by itself, do all the math I want with y by itself, and I don't have to worry about what's happening in the other direction, right? If I'm moving horizontally, I'm not moving vertically. If I'm moving vertically, I'm not moving horizontally. So while my problem might say that I'm moving diagonally, if I break that up into two pieces, I can pretend like I just moved horizontally, and then like I just moved vertically, and combine them back together. So what we end up doing is we break the quantities into components. We solve for each direction individually using those components. And then if the problem asks for it or if it's necessary, recombine using trigonometry. So let's look at an example here. And there's a lot of writing here, but I'll break it down for you. It's more obscure or maybe less clear than you would expect on like an AP problem, but because I knew I was going to walk you through it, I was more concerned about writing the question than about, getting the thoughts down than about making sure it's super easy to understand on its own. So a river is flowing at a rate of 2 meters per second. So I'm going to draw that here, a river. And I'm going to label the velocity of the river to be equal to 2 meters per second. An amateur boat pilot wants to cross this river in their boat. They know that if they want, they'll need to point their boat upstream if they want to end up directly across the river. So basically they need to sail in that direction because the river is going to pull them to the right. So they need to sail to the left so that that way they'll hopefully land, straight across. But because they're an amateur, they don't know exactly how far to aim, and they just give a guess of 15 degrees. So this direction right here is 15 degrees. They then proceed at a speed of 5 meters per second. So V of the boat is equal to 5 meters per second relative to the water. If the river is 20 meters across, so I'll call this delta Y equals 20 meters. How far upstream or downstream do they end up? So there's a lot here. Let's just look at the pieces though. So the main thing I want to do is look at this velocity of the boat. So Vy is going to equal Vb times cosine of theta. And Vx is going to equal Vb times sine of theta. Now this is going to be a negative Vb because we know from just looking at our diagram that this is pointed in the negative direction. So now I've got the velocity of the boat broken into its components, Vx and Vy. So we need to find out, where am I going to end up on the far side? Well, we know that the total velocity in the x direction will equal to Vx plus Vr, right? Because basically the boat and the river are kind of duking it out speed-wise. So that would be Vr minus Vb sine theta. And then because the river is not flowing at all, crossways, we just have to worry about the velocity in the y direction. It's just in the y direction. If we look at the y distance and the y velocity, we can find out how long it takes to cross the river, and then we can just multiply it by this total distance. So our delta x is going to equal the velocity total in the x direction times delta t, and my delta y is going to equal the velocity in the y direction times delta t, and these delta t's are the same. So what that means is I can rearrange this delta y, delta t equation to get delta y over Vy, which is also equal to delta y over Vb cosine theta. And then that can be plugged into this top equation to get delta x is equal to Vr minus Vb sine theta times delta y over Vb times cosine theta. And this will tell you how far they end up in the x or y direction. Let's check our units real quick. Vr will have units of meters per second. Vb will have units of meters per second, so I can subtract those. That's totally fine. Vb will have units of meters per second, which will cancel with these two units will end up canceling. Vb can't cancel because it's not in both terms, but the units will cancel, and I'm left with just meters on the top. So this looks like a pretty good expression. We know Vr, we know Vb, we know delta y, we know theta, so we can plug this in and we'll get a number. But like I said before, I just don't have a calculator here, so I'll leave that as an exercise for you to actually calculate it. But that's the idea behind 2D kinematics. We broke it into components. We dealt with the y stuff, we dealt with the x stuff, and then we combined them back at the end.